Hello. I have a question, which is, did we say that today we would be doing projectiles or moments? Because I can't remember. We would look this week. Our aim is finish all of the notes, finish all of the content for stats and mechanics. I did worry that it was projectiles because I've set up moments now. So yeah, aim for this week is all of this is totally done. And don't forget, this is worth 1/3 of the A level, right? All of the pure is worth 2/3. So this is small fry compared with the other things. If you look at the overall number of marks that you're going to get, the big red ones, they're still much lower than things like trigonometry, differentiation, integration, lines and circles, quadratics. All of that stuff is worth more marks as an individual topic than these ones. If you were going to just only learn a couple of things, if you learn normal binomial hypothesis testing, SUVAT, projectiles and connected particles, and just don't worry about anything else, you're still going to get almost all of the marks. Okay, so option 1 is that we look at some moments problems, because that is what I thought we were doing and I set that up. So how many moments problems have I got? These 3 moments problems. This one, they're classics basically. This one, and this one. But I would need to do another one as well on friction. So I was going to do that tomorrow, the friction moments with the friction in general, because friction in moments doesn't happen in AQA. So option 1 is that we do moments, and option 2 is that I do projectiles, but we just grab some random questions and I haven't prepared it basically. Sorry about that. I knew we discussed it and then I didn't write down what we were doing. And then the aim is that by the end of this week, binomial distribution is okay, normal distribution is okay. You know how to do the hypothesis test for a binomial, you know how to do the hypothesis test for a normal, and you know how to do the hypothesis test for correlation. And that probability, you've reminded yourself about what you need to know about probability from the first year, like what are independent and mutually exclusive events, the fact that it all adds up to 1. And then also added on this second year thing, which is the conditional probability formula, which is this one here. Probability of A given B is probability of A and B over the probability of B. And that's all the mechanics done. There's a little, I think we're 50-50 on moments and projectiles. I honestly don't mind. I don't mind which. Let's see, what is the current weighting? Projectiles, projectiles, projectile. No, that was you telling me what you want. Moments, 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 projectiles, moments, projectiles, projectiles, moments. Right, moments as 1. We'll do moments and then we'll do projectiles tomorrow. Moments. Okay. So, but what day is it actually? Is it Thursday? I literally have lost track. It's so weird. I think it's Thursday. So, the end of this week, you could either call that tomorrow, as in you've got today and tomorrow, or you could call it Sunday, in which you've got today and then 3 more days. It's up to you what you want to consider the end of the week, okay? But we are going to, as a group, move on this week from talking about filling in gaps and going over the content to, I think it's Thursday. We're going to move on to starting to make progress with your progress charts and stuff like that next week. Okay, so your aim really is to make sure that all of the stuff on here is ticked off. You don't need to be really good at it, but just make some notes and have a vague idea. And then similarly with the pure, if you go back to oh, I can't get it now, but go back to what we did a week ago on Monday, so 10 days ago, that whole pure on 1 page. You can get that in the Exambulance as well. TT method, I'm going to be doing with you in detail, and that is going to be from next Monday, but I'll talk to you about it tomorrow so that you can get going, and I'm going to do the whole detail with you. Okay, moments. So there are 2 ways to think about moments. One of them is that they're a completely separate topic, called moments. And another one is that it's a tiny extension of just doing a normal force diagram, force acceleration diagram. And I think the reason that I've pulled it apart and called it its own topic is partly, integration. Yeah, I forgot. I'll make some up after I've told you this. Good point. And timer, go. Right, the reason I pulled it apart is partly because I think that step 2 about the moments, where you're actually finding the moments to create the equation, that does actually take quite a lot of practice and not so much understanding, but practice and developing your skills and techniques. And the other reason that I would pull it out as a separate thing is that I know that lots and lots and lots of teachers leave it till the last minute to do moments. So that means that it's something that is generally taught quite fast, too fast, you might argue, and something that students come away going like, whoa, I don't really know what was happening there. So that's the reasons why I've pulled it apart. It's not pulled apart because it's worth lots and lots of marks, because it isn't worth lots and lots of marks. It's worth a lot less than these ones. So the biggest marks are SUVAT projectiles, connected particles, F equals ma, something on a slope, thing with a pulley. That's what's worth the most marks. Right, before we go into looking at what you do for each thing for moments, we will just chuck in a little extra fun integration. You're completely right, we should always do integration. So the integrals I'm going to be giving you, they might be from the 10. So you know what sine, cos, sec squared, cosec cot, sec tan, and cosec squared, and e to the, and a to the, and 1 over, and something to the power of n. All of those, you know what got differentiated. Next ones you're looking for is a fraction with something on the bottom and its derivative on the top, or e to the something with the derivative next to it, or trig of something, doesn't have to be sine, with the derivative next to it, or what's the last one? Powers. So something to a power with the derivative in front of it. And all of those ones, you know what got differentiated, okay? Or hopefully you do. Next stage that you're looking for is the squared trig ones. So we've got 2 of them here, sec squared, cosec squared, and it's the other ones. So it's sine squared, cos squared, tan squared, and cot squared. Those are all the things that you should just know how to do. Then it moves on, the integration moves on to things that aren't any of those. So for example, you might have a fraction that is none of those. You've got options. You could use division, or the little trick I showed you, or you could use partial fractions. You also have the situations in which you might need parts. There are 3 situations in which case you might need integration by parts. One of them is anything to do with learn. One of them is where you've got stuff to do with x, and then e to the stuff to do with x. And the other one is stuff to do with x, and then trig of stuff to do with x. Those are the situations in which you'd need parts. The only other thing that we've got in our sort of arsenal of ways of attacking an integral is substitution. Now, substitution is a hard one, and it takes a long time to sort of be able to recognize them. They might tell you the substitution, which would be nice, but there are ones that you do need to be able to recognize. So this one is the hardest one, the substitution, but it's very rare. Okay, here they are. How mean shall I be to you today? Not that mean, I think, because moments are quite difficult. I will give you 1 minus cos squared x over 3. And I will give you, I'm not going to do that one because I don't want to. I'm going to give you u plus 1 all over 2u minus 3 du. And I'm going to give you ln x over 2 And that's all. Just those three. Okay. I think I'm going to give you, I think 3 minutes is too much. I'll give you 2.5. Right, 1 more minute. So I'm going to put some decline. Put it on do not disturb. Although the iPad will still disturb, won't it? I don't know how to do that one. I'll just hang up. Right, here's the hints. Okay. Let's talk these through. So cos squared is one that I want you to just be able to do, just know. So cos squared x is one of our squared trig functions. You always just replace the cos squared with 1/2 plus 1/2 cos, and then you double the angle. If it was sine squared, you change it to 1/2 minus 1/2 cos, and then you double the angle. So what we're actually integrating here is 2/3 x in there. I doubled it, and I'm writing it as 2/3 x rather than 2x over 3 deliberately. Subtle difference, but 2/3 x, it really shows me when I use the chain rule what it is that's going to be the derivative, what's in front of the x. I've used big square brackets round to make sure that that minus in front of the cos squared applies to everything. Okay, so altogether I'll be doing 1 minus 1/2 is 1/2, and then it will be minus 1/2 cos 2/3 x. So what's likely to go wrong here is minus signs rather than anything else. The answer to this one is 1/2 x. Now I'm going to go all the way over here and think about this slowly. Obviously, what got differentiated is sine 2/3 x, okay? That is what was differentiated. Sine differentiated is cos. So sine got differentiated. Now I need a 1/2 out the front because otherwise I wouldn't have that 1/2 there. But I also need something to deal with the fact that when I differentiate sine 2/3 x, a 2/3 will pop out. And I don't want a 2/3. So the chain rule, when I'm differentiating, which is the only thing I'm thinking about here, is differentiating in that direction. That 2/3 will pop out, and I don't want that 2/3. There is no 2/3 at the beginning here. I don't want it. So I'm going to put that 2/3 here upside down. And then that means that when that 2/3 comes out, when I'm differentiating, it will hit the 3/2, they'll cancel and it's not a problem. Right, now I want to think about the sign at the front. So the minus or the plus. So when I differentiate sign, I get cos, no sign changes happen or anything like that. So if there's a minus here, then it will be a minus there. So that's what I want there. Now notice everything, all of my thought process is there. Once I've done the trig, cos squared is a half 1 plus cos 2x. Once I've done that trig, the actual process of integrating is actually just differentiating. So altogether, the answer would be 1/2 x minus 3/4 sine 2/3 x plus c. Now, the parts. Anything to do with ln, we need parts. So it's going to be u equals the ln bit. And again, look, I'm going to write it as a 1/2 x, not x over 2. It's just much cleaner to see what the derivative is if I've got an amount of x's. So when I differentiate that, right, chain rule, differentiation, differentiation, differentiation. Ln goes to 1/. Now I multiply by the derivative of that thing inside. That's what the chain rule tells me to do. So I multiply by the derivative of a 1/2 x. And a 1/2 x differentiated is a 1/2. Now, when I do times by a 1/2, I can put it on the top, or I can do it like this, times 1/2. So either way, when you'd write it this way, on the top you've got 1, on the bottom you've got 1/2 x times 2, which is just x. So any way that you think about this, you're going to get 1/x as the derivative. Then we go across, so we've gone down differentiating. Now we go across and we write down what the derivative of v is. That's just the number 1. It's invisible, but we put it there. Whenever we've got ln, we just stick a 1 at the front if we need to, so that we can do parts, so that we've got two things to times together. This is the thing about parts. People use it when it's a product, like this times this, and most of the time a product is not anything to do with parts, but one that is parts always is ln, and there's no product. But it is parts. So v prime is going to be 1, and then when you integrate it, you get x. So this is what the ingredients look like for our parts. And then the formula is uv minus integral v du. And I do obviously know that formula, uv minus integral v du, which is why I can say it quickly, but I usually, honestly, this is true, I write this down. uv minus integral v du, I write those down and then I look at it. And I go, right, the top is x times ln x over 2. uv minus integral, and now it's these two times together. And that times that is 1. And therefore the answer is that. So what did we need to be able to do for that? We needed to know for sure that anything to do with the ln is parts. We needed to know how to get the parts ingredients and how to write down the actual equation once you've done the parts. And the parts involve differentiating ln and using the chain rule and integrating the number 1. And then here again, we had to integrate the number 1. So integration wise, what did I use? A formula for parts, that's it. And integrating the number 1. Okay, this one is the sneaky trick, okay? So you can use division. The division would look like this if you did synthetic division. You would be, it's a bit of a pain, but you do, I've got 1 u and 1 1, that's there and there. The thing that makes the bottom 0 is 3/2. You would put the 1 here, then you multiply these two together and put it there, and then you add those up, and that's the remainder. But what you have to remember with the synthetic division, if there is a number down here, if there's a fraction, so if there's a number there, then the quotient that pops out, which is this guy here, that's the quotient, it has to be divided by that number. It has to be divided by 2. The remainder is fine, but we have to divide that quotient by 2. So actually, what we're going to get, if you use the synthetic division, is, I want blue, that this guy here, u plus 1 over 2u minus 3 is equal to 1/2, that's that guy, add 5 over 2, still on top of 2u minus 3. That's not very nice, so I probably would multiply the top and bottom of this one by 2, like that, times 2, because otherwise it's a little bit disgusting. Fractions in fractions are not fun. So here it would cancel, and then that would be times 2 on the bottom. So it would look like that. So the 5 over 2 that pops out as the quotient, it's nicer to write it like this rather than putting it on the top, but either. Now I'm going to show you how you can do that without using synthetic division, like this. So what I did, the sneaky trick, and I've shown you this a couple of times, synthetic division and algebraic division are the same if you, they're the same if you're dividing by something linear, but algebraic division, you can divide by quadratics. But in the new spec, you won't be asked to divide by quadratic. It specifically says that you will only be asked to divide by something linear, and therefore you don't need algebraic division, you only need synthetic division. But you can use whichever one you prefer. U prime was x for ln x. No. When you're using parts to do ln, you always have ln as the u, because you can't integrate it. If you could integrate it, you wouldn't be using parts to integrate it. So you can't use ln is the v prime and then integrate it. You have to use u as ln. Always, always, always the u is ln, and then you differentiate ln, because you can differentiate ln, but you can't integrate ln. Otherwise, we'd be able to integrate it. That's why the ln is there, and then you differentiate it. So the sneaky trick is this. See what's on the bottom, 2u minus 3. We want that on the top. So what I've done is literally just put it on the top there. And then I put at the front whatever I needed to put at the front to make it match this. See, that's 1u. So because that says 2u, I need a half here. So when I expand that out, it will say u. That's that guy. Then I want it to say plus 1. Now at the moment, if I expand this out, it says minus 3 halves. Minus 3 halves. Now I actually want it to be plus 1. So how am I going to get it to be plus 1? I'm going to have to put on the end of there plus 5 over 2. And then you can use the v, and then you see that we get exactly what we've got here. Half 2u minus 3 over 2u minus 3 is just a half, which is there, which is what pops out here. We halved it because of that 2 down there. And then the other bit, 5 over 2u minus 3 was the bit that we got here. So there's 2 ways of doing it, synthetic division and sneaky little trick thing. Sneaky little trick is sometimes faster. Either of them is fine. So the answer is 1/2 x. Now I'm going to leave a gap. I'm going to put ln 2u minus 3 because that's obviously what was differentiated. If you differentiate ln, you get 1 over. There's a 5 over 2 at the front. And I also need to put a half in because I don't want this 2 coming out with the chain rule. If I differentiate ln 2u minus 3, I get 1 over 2u minus 3 multiplied by 2. And I don't want that 2. So I put a half there. And that's the end. That is our integration for today. Now let's look at moments. Where are the moments? Here we go. Okay. What is difficult about moments? Well, drawing the forces on, we could argue that drawing the forces on is difficult. Is it though? Is it though? No, it's not that difficult. Then once we've drawn the forces on, we can form the equation all the ups equal all the downs. Is that hard? No, definitely not. Anything pointing up equals anything pointing down because we're in equilibrium. Maybe we need to do resolving a force. Is that hard? No. Resolving a force just means splitting it up into its perpendicular thing. And then once you've split it up into its perpendicular bits, like that one and that one, then you work out where an angle is. This is now a little bit tricky. Let's say the angle is there, and this is the force T. Then the one next to it, adjacent to it, the one where the alpha is touching, that one's cos, and the other one's sine. So yeah, maybe resolving force is a little bit tricky. Left is right. All the forces pointing left equal all the forces pointing right. Is that hard? No, you just look at your diagram. And then moments equations. Now, moments equations, the actual moment is sometimes difficult. Why is the actual moment difficult? Because you have to work out the perpendicular distance from the point to the line of action of the force. So all of the moments that we do are going to look something like this. Here's the force. Here's the point I'm taking moments about. And I need to find the perpendicular distance from the point I'm taking moments about to the line of action of the force. And that D tends to be what's difficult. And then we multiply those two together. Actually, let's call this F. We multiply these two together to get the moment. Now, someone asked me in the course today, how do you know whether it's a clockwise or an anti-clockwise moment? If you do all of your moments individually like this, it's really easy. You follow your pen along the force towards the arrow, and then you spin around the A, and you just look at it until you think, is that the way a clock goes, or is that the opposite of a way a clock goes? It usually takes me about 2 seconds to think that is the way a clock goes. So that's clockwise. Okay. Resolving forces you have covered, I just showed you, literally. Resolving forces is the force that's not going in the direction you want, put two forces either side of it so that the force not going in the direction you want is in the middle. Then find out what that angle is or what that angle is. And then the one next to the angle is T cos and the one not next to the angle is T sine. That's it. Okay, that's literally resolving forces. And then for moments, we're going to make three equations. Equation 1, up is down. Equation 2, left is right. And equations 3, clockwise equals anti-clockwise. And really the big bit of advice that I'm going to give you is to do your moments individually. Give them their own space, their own little world. Give them their own thought, their own time. Each moment, give it its own little box. Okay, I'm just going to answer the question about the integration by parts. When you differentiate it, it wouldn't go back to what it was before. Now, if you're right, Luca, then I differentiated it. Then I integrated it wrong. You're completely right, but I don't think I did. So let's have a look. What happens if you differentiate this? Make some space. Space, space, space. The derivative of x ln x over 2 minus x. We need the product rule, first of all. Product rule. Hold still the x while you differentiate the ln x over 2. The derivative of ln x over 2 is 1 over, I'm going to write it as a half x instead of x over 2, and then you multiply by a half. So that half cancels with that half, leaving me with just 1 over x times x, which is 1. Minus, when you differentiate x, you get 1. This is a good, no, I didn't do the product rule. I was like, whoa, wait a sec, it doesn't work. I forgot to do the product rule. The product rule says we hold the x still while we differentiate the ln x over 2. Then we put a plus. Then we hold still the ln x over 2 while we differentiate the x. There we go. So 1 add ln a half x minus 1 equals ln a half x, which is what we were trying to get. So it does work. Okay. Right. Yep, you can use late with integration by parts, but so it's which one is u? Logs, algebra, trig, exponentials in that order. Log. So ln, if there's a ln, that is the u. If there's no ln, then the x or the x squared bit is the u. If there's no logs and no algebra, then the trig bit is the u, but you won't even get that far because it won't be. Okay, so apprentice question. Up is down, left is right, moments is moments, but we need to start by putting the forces on. And this is the bit that actually, I think this is where moments usually goes wrong. So I'll focus on that bit first for each of the diagrams. Okay, uniform plank. That means that the weight is in the middle. If the weight is in the middle, then the weight is there. And the weight is 15g. Okay. There is a woman of mass 50 kilograms standing on the part of the plank which is projected over the water. So let's say that the woman is here. Now, here's an important thing. What I'm modeling here is a plank woman. You know, like how in forces sometimes you talk about a lift man, it's the lift and the man. This is not a rod and then looking at the forces on the rod and the woman putting a force on the rod. So there is no reaction force at the woman. It's a piece of plasticine with a blob on one end. So it's a non-uniform rod, basically, is what we're modeling. The thing that we're modeling, the whole system, is the plank and the woman made out of one piece of plasticine. Now, the center of mass of that entire thing is not the middle, but we can model the center of mass separately for each of the different bits of the weight. So the 15g that I've drawn on, that's the weight of the wooden part of the plank woman. Okay, the plank woman is one object, plank woman. The plank part of the plank woman is uniform, so its weight comes from the center 15g. The woman part of the plank woman, its weight is centered right here, like that. But there's no reaction because the woman is part of the plank woman that we are modeling. That's really, really important. No reaction. That's a common mistake. Okay, other forces. There is one other force. Exactly, where's the pivot? Now, this is really tricky, right? Basically, in this situation, the reaction could be anywhere. The reaction could be bang in the middle here. It could be all the way across. It's going to move across and move across and move across to the point where it's like, oh, it's about to tilt, literally about to tilt. And at that point, the reaction is going to be on the touch point here. Like that. Find the greatest distance from the riverbank at which she can safely stand. So we've assumed she'd like walked and walked and walked and walked to the point where it is just about to tilt around that point there. But it's not actually tilting, it's almost tilting. It's about to tilt, and that's why that reaction is happening at that point. If it wasn't about to tilt, the reaction would be further left and we wouldn't know exactly where it was, okay? So that's our situation. Up is down, R is 15G, add 50G. Done. Now we know what R is. Left is right. Done. There's no left forces. There's no right forces. Do I need to resolve any diagonal forces? No. The woman doesn't have the normal reaction because we're not, this is really, really key. We are not modeling the plank and the forces on the plank. If we were modeling the plank and the forces on the plank, then there would be a reaction. But what we're modeling is the plank woman. The plank woman looks like this. That is the plank woman. It's one object. They've been merged. The plank part of the plank woman has its mass uniformly distributed. So its mass comes from the center of the plank woman. But the woman part of the plank woman, its mass is all focused all down one end at one particular point. So the mass of the woman part of the plank woman comes from a different place. But the thing we are modeling is a plank woman. It's all one object. They've been merged together. It's just their masses, that we can split the masses up into the planky part of the plank woman and the womany part of the plank woman. And that's why there's no reaction, because it's an internal reaction. We're modeling the plank woman. Okay, really, really important. No reaction. The reaction is between the plank and the edge of the riverbank. And because we're modeling it as about to tilt, all of that reaction is focused down at that one point where they're touching. Right, I don't want to spend too long on this one because it's an apprentice one and I want to build it up a little bit. But I'm going to show you what I mean about doing all of your moments differently. So I'm going to take moments about here. I'm going to call that point X. And I'm going to take moments about there. There are only two forces which don't go through X. So the line of action of R is through X. So we can forget about that. There's this one here and there's this one here. And I'm going to give them their own little world always. Here's one. There's X and there's the 15G and there's the perpendicular distance. Don't let anything else confuse you. That's just the world of that moment. I'm taking moments about X and I have one force. Next, I'm taking moments about X and I'm considering this force. Now, what I need to think about, and this is sometimes the really, really hard bit, is this D. In this case, it's not too difficult, right? Let's look at the diagram. How far is it from there to there? How far is it from there to there? Well, we're trying to find out how far it is. So we could call this distance here, we could call it D actually. Let's call it D. So that's D there. D is the distance that we're trying to work out. Right, how far is it from X to the 15G? Well, this whole thing here is 5. And from there to there is 3, because there's 2 on the end. And from here to here is D, because that's what we called it. So this bit is 3 plus D. This moment, follow down and then woo, 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 woo. That is an anti-clockwise moment. That's going the wrong way around. This one, follow the line down, spin around the X, that's going clockwise. So this moment equals this moment. 15G times 3 plus D equals 50G times D. Cancel the G's, blah, 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 solve, solve, solve. Okay, this method just works every single time. Okay, I am going to move on to the next one because that gives you a general idea of what I'm talking about. Right, no picture. Why is it 3 plus D? I just explained that, why it was 3 plus D, to do with the distances. Right, let's draw this one. So we're going to be drawing the, let's think of it as the ABC plank, right? We're modeling the ABC plank. Isn't it just 3M for the 15G? Let me see if I went wrong. Three. Oh yeah, you're completely right. All right, apologies to Ruhab. I didn't explain, I did get it right. But maybe I did that deliberately to make a point of the fact that the hardest thing and the thing that goes wrong the most often is D. Actually, you are completely right. The thing that I'm right, the thing that goes wrong most is D. And I did a nice little demonstration of it there by going wrong with D. So here is X, here is the line of action of the force. That is 3, that D shouldn't be there. So this wouldn't be here and now you can find D. Yes, boom, totally, completely right. I agree with you. Although I did highlight my point about D being most difficult. Right, this is going to be a quickie now because it's really similar, but I wanted to show you it because it is it's a sort of typical question that you might see. So we've got our uniform rod, AB, like that. It's uniform, so its mass is coming from the center. And it's got mass 4 kilograms. Don't worry about distances for now. The distance bit is more tricky, so I don't want to put it all over this diagram. It's got 3 masses attached to it. A mass at the end here at A, and a mass at the, and that's 5G. And a mass at the end B, 3K, no, that's 3. This one's 5. And then there's another one here, which is 8. So what we're modeling is the ABC plank. Like before we had a woman plank, plank woman, this is the ABC plank. It's all one object. Its mass is not uniform. The mass of the planky part of the ABC plank is uniform. Just the planky part of the ABC plank, that's got uniform, that's a uniformly distributed mass. So we model that mass coming from the center, that's the 4G. But the A part of the ABC plank has got all its mass focused at one point. And so is the B and so is the C. So there's no reaction forces because nothing is sitting on something else. Very good question. How do I know which side C is? I don't know, but it doesn't matter because what I'm going to do is I'm going to measure this one as being D. And if it comes out negative, then it was on the other side. Okay. If D comes out to be negative, all that means is it should have been on the other side. Now, how am I going to do up is down here? How does this make any sense? We've got all these downward forces. We've got a massive resultant downward force. This must be accelerating downwards. There is no up. Up is not down. It makes no sense. And the point here is that we're trying to find the center of mass of the whole system. Now, what is a center of mass? The best way to think about it is, here's your finger. That's a hand. I'm not sure which way a hand would go, but there's your hand doing this, right? The center of mass is where you put, where it would balance, right? Where it would balance. That's where the center of mass is. Now, this is actually a good example of a woman plank, because I've got a relatively uniform pen here, but it's got this thing on the end of it. So the center of mass of the pen is modeled as the middle, but because there's got this other bit whose center of mass is coming from there, then the center of mass of the system would probably move across. If I wanted to balance this on my finger, I probably would go left a little bit like that. Now, what we're going to do is imagine that somebody is balancing this thing, this ABC rod on their finger, and that force upwards is creating a zero moment of the whole thing. So I'm going to put on the center of mass is, say, where would it be? The center of mass would probably be like here, maybe, or like there. There's the center of mass. And the center of mass is the point at which, if I put a force there, then all these other forces all balance perfectly. There's no rotation happening at all. So when it talks about the center of mass, that's what it's talking about. All of those different masses all combined like this. Okay, so that's the setup. That's kind of the hard bit. Once we've got the forces diagram set up, which is kind of the hard bit, do we need to resolve any forces? No. Good. Nothing's going diagonal, so that's great. We don't have to resolve any forces. We're going to do up is down. We're not going to bother with left is right because there's no left and right forces, so we don't need to bother with that. And we don't need to bother with this. We do up is down, and then we're going to do individual moments about some point. Okay, right. Up is down. R equals, this is equation 1. R equals 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 15, 20. No, they don't all have an R. This is what's really important, for the same reason that the woman, the plank woman, doesn't have an R. If I say I need something that's like non-uniform. I'm modeling, well, just think of it in terms of plasticine, right? Imagine this pen is made of plasticine and I get a blob of plasticine and I dump it on the end, right? That is the object that we are modeling. The whole thing, we're not modeling a rod, we're modeling a rod woman or an ABC rod. It's got things on it already. We're not modeling the rod and the rod is feeling a force of the thing pushing on it. The thing is part of the whole system. So let's say I am modeling myself. So I stand on the floor. There's me standing on the floor. What forces do I feel? I feel my weight going down and I feel the reaction from the floor. Right, now, I'm now holding a cup of coffee. How has the diagram changed? There's no reaction force here because me and the cup of coffee are now one object. If I'm modeling just me, my hand, and this is the coffee cup, and I'm modeling my hand, what forces does my hand feel? My hand feels the weight of the coffee and the reaction. Or rather the coffee cup does. But in this case, what we are actually modeling, and this is always, always true, and it is a very common mistake at the beginning, and I think it's because the moments gets kind of rushed at the end, so there isn't time to go into this, the fact that what we are modeling is everything as one block. That's why I've drawn it all in black. the ABC rod or the woman rod? Right, moments. This is what it's going to look like. I'm going to take moments about here. What do I want to find? The distance AC. The center of mass is 4.3 meters from A. So this is 4.3 meters from A all the way across to the center of mass, which is where that R is going up. That's 4.3. And I'm trying to find, what am I trying to find? Distance A to C. A to C. Oh, right. So I'm trying to find this distance, which is actually the same as finding this distance, right? I could find that distance there and then just add it on to 4.3. Anyway, regardless, doesn't matter. What we're going to do is moments. So I'm going to do, where would you like me to do moments about? You can have A, B, C, D, or X. I can do moments about wherever you like, A, B, C, D, or X. I'll just take the first one that comes, A. Right, I'm doing moments about A. Here's A. A, line of action of force, moment number 1. A, line of action of force, moment number 2. That's this one and this one. There's also this one. A, line of action of force. And there's also this one. A, line of action of force. Right, now we do the difficult bit, which is the D. D for difficult. How far is that? How far is that? How far is that? And how far is that? Okay, from A to the 4G is half of the length of the entire thing. The entire thing was 6, so that's 3. What about from A to the center of mass? Well, we know that from A to the center of mass is 4.3. What about from A across to the 8G? Well, that's what we don't know. I'm calling it 4.3 plus D, or we could just call it X. Let's just call it X. Let's say that's X. That's what we're trying to find. So that's X. A to the 5G, that's all the way across the 6 meters, so that's 6. Clockwise or anti-clockwise? Follow the line down. Ooh, clockwise, clockwise, anti-clockwise, clockwise. So this one and this one and this one, those moments equal this one. So the equation that we would get is 12G plus 8XG plus 30G equals 4.3 times 20G. And then we can solve that to find X. Done. Right. Hinges. Hinges are very simple. Do not worry about hinges. In the situation where we have a hinge, the modeling that we do is that we make it into 2 parts. We make it into an up, down, and a left, right. Now the right left part will always be right. And this is the force at the hinge, okay? 4.3 was in the question, it told us the 4.3. So at the hinge, what you do is you put on an X and you put on a Y. Now the Y, it doesn't matter whether you put it up or down, okay? It really doesn't matter. If you put it up and it comes out that it meant to be down, your Y will come out negative. If you put it down and it was meant to be up, it'll come out negative. If you happen to put it the right way, it'll come out positive. So just put it whichever way you fancy putting it. That's what we do with a hinge. Everything else is the same as it was before, but put the forces on is sometimes the difficult bit. So let's have a look. We have got a uniform beam. So that means that the weight is going to come out of the middle. The beam is hinged. We've dealt with the hinge. There's a strut, and the force exerted on the beam by the strut goes in this direction. That's a bad direction. We're going to have to resolve that, guy. And the beam carries a load of weight 50 at the end. Weight 50, not mass 50, weight 50. Yes, AQA do need to know hinges. The only thing AQA don't need is friction inside moments, but you still need friction. So the difference between AQA and the other two boards is that AQA have specifically said we won't test friction in the same question as moments. We will still test friction, we will still test moments, but we will not test friction and moments in the same question, in the same scenario, in the same setup. So that means that you can't, yes, you're completely right, it's not 70G, it's 70 because it's the weight. Right. The timer is going. I'm going to briefly break the rules for 4 minutes and then stop because I want to show you how this works. Okay, so what you need to know is that at a hinge, you do one right and one up or one down, up to you. Everything else is just the same as normal, but I need to deal with the tension, what's the opposite tension? The thrust force in the strut. So you've got two options when you're setting these questions for students, you've got two options. There's the wall, there's the hinge. You can either tie a piece of string to the wall and extend the piece of string down like that, and that's what is holding the thing up. That's option 1. Option 2 is what they've done here. So here's the hinge, here's the thing, and they put a bracket, basically. They put a piece of wood here. There's the piece of wood. Now that piece of wood is pushing in to the rod thing, the rod woman, the rod block, whatever it is. It's pushing in, and we never ever model forces going into the thing that they're acting on. It's always coming out. So even though the actual diagram looks like that, the force is going in that direction, and the force would be thrust. It's pushing. Whereas this one, the force is going in the direction of the string, and that's tension. Not that it particularly matters, that we just call it T probably. So those are the two forces. So done the forces, told you what to do with the hinge. We've now got our forces on. We can do up is down, left is right, moments about any point. We do all our moments individually in their own little box, but we need to do the resolve. That diagonal one is no good like that. I need to split it up into how much up and how much across. So this is how we resolve forces. It's not a big deal. You draw the up and the across so that the one that you're resolving is in the middle of those two. So we wouldn't go left or down. We want the blue ones either side of the red one. Now I need to work out what angle that is or what angle that is. Now they tell me something here. What do they tell me? Oh, no, they don't tell me, but they tell me that distance and they tell me that distance. So I can work out this angle using trig, normal trig, right? If I tell you that that's 0.5 and I tell you that this is 1.3, the hypotenuse, and this is theta, then sine theta is the opposite over the hypotenuse. So now I know what theta is, and whatever that theta is down there, it will be the same as this theta here. So if this is the T for the thrust coming from the bracket thing, then the bits it gets split up into, the one next to the angle is going to be cos, and the other one is going to be sine. Now you can get cos theta in a couple of ways. You can get cos theta by using Pythagoras to get this length, that squared plus that squared is that squared, and then cos theta will be that length over 1.3, adjacent over hypotenuse, so you know what tan. Now we know what cos theta is, we know what sine theta is, so we can put the blue ones on, and now the red one becomes irrelevant. And that, what I just did, is really the hardest bit, resolving the forces and drawing the diagram, because now up is down. So equation 1 is going to be y add t cos theta equals 70 add 50. This is not a very tough moments question. No, there's much harder than this. That's why it says apprentice. But moments is tough until you start practicing. But what I'm trying to show you is that it's always the same. You get your forces on. If you can get that right and then resolve any forces, then it's always the same. Up is down, left is right, and you can see that my X is going the wrong way. So my X can't go that way, because if it did, then I'd be having nothing going right. Must go like that. X is right. So X is T sine theta. And up is down. So Y and T cos theta equal 70 and 50. And then moments. Now the point I would probably do moments around here is A. So let me show you what they look like. Individual one. Here's A. Here's the line of action of a force I need to take into account. Here's A. Here's a line of action of a force. Here's A. Here's the line of action of a force. All of the other forces go through A, so there's no moment. So here's A. We've got this force, this force, this force. Clockwise or anti-clockwise? This one, clockwise. This one, clockwise. This one, ooh, anti-clockwise. What's the hardest bit? The hardest bit is working out that distance there. That's the hard bit. And that's why by giving them their own little world, you make it much, much easier for your brain to just focus on the difficult bit, which is finding D. Once you've done that, you've got up is down, left is right, moments equals moments, and then it's simultaneous equations. So my target for you for the next 24 hours is to go into the content guide, which you've all got, because in the exambulance you can click on content guide. Go to the moments bit and you will see these ones here. Work your way through those and just make notes. Okay, just that for 24 hours. They're about 10 minutes each. So that's 20, 30, 40, probably just over an hour. But AQA students, anything, you definitely don't need ladders. And any question that's got anything about friction, AQA, you don't need specifically, because you're not going to be doing friction in the same question as moments. Right, I need to go, or Rich will not be able to do chemistry, and that will be a disaster. Have 24 hours playing with moments. Don't forget your target for the end of this week is to finish all of your A-level maths notes, and I will see you either at 4 o'clock in the exambulance where it says schedule for study with me, or I'll see you tomorrow at 1.